Did you have any specific questions, or was it mostly just like kind of getting a review?
I don't understand Chapter 9 at all. So
okay.
Literally anything you want to go over.
All right, that's fine. Okay. Let's see. How do I want to go over this?
This is the one with the peaks and the. Right?
No, that's chapter 10.
That's 10.
Would you rather? Because 9 is alcohols and ethers, but like the reactions. But you already had a quiz on this.
Yeah, that's
fine. Okay. Yeah, 10 is like a curveball, you know, a shot to the right field. It doesn't really align with a lot of the stuff that you've already reviewed, so I figured more people would want to go over this. And you had a take-home quiz on this.
I have not done it yet, but yes, it's due tomorrow.
Okay, all right. Got it. Okay.
It's very, yeah, ambiguous. The questions are kind of all over the place.
So before we get started, just so we're clear, if you have questions, that's fine, but please make sure that none of those questions are on that take-home. Right?
No, I haven't even...
Okay, yeah. I trust you. I just gotta put it out there.
I get it.
All right. So NMR, nuclear, magnetic resonance. So when you think of NMR, a real-world example of this would be like an MRI machine.
Okay.
Okay. It's the same type of process. It's just one we use for imaging. This is a little bit different because you're looking at very, very small things. Mm-hmm. But you can get a lot of information from this that you can't get from other physical property tests. So this is really important for organic chemists to figure out the really differences between two molecules if they're in a mixture and knowing what's in that mixture. So nuclear, there's going to be radiation used. Okay. Now the textbook goes into a lot of detail as to how the radiation works and what's actually occurring, but essentially the readout that you get is the effect of nuclei absorbing this radiation. When the nuclei absorb, you see a peak on your readout, and that tells you, depending on how much radiation and what the frequency is, that tells you exactly what is giving you that frequency. Okay, so there are some things just in general that you need to know. He likes you to have a very general understanding of how this works. So, for example, so you have these superconducting magnets, okay? These magnets get very hot. So they are cooled by liquid helium. And this helium is kept cool by liquid nitrogen. Just kind of some, random things that he wants you to know. Okay. So these points you should know. Only certain atoms are active in the NMR, okay? So to be active, you had to have an odd number of protons or neutrons. You are inactive when you have even numbers of both.
So active and inactive, meaning active is going to show a peak, inactive will not?
Yes, active peak, inactive no peaks. Okay. Yep. So some examples of things that are active. So if we look at hydrogen, how many protons does hydrogen have? One. How many neutrons?
One?
0. Helium has 1 proton. Oh, sorry. Wait a second. No, it's 0. Sorry, 0. Because the hydrogen atom only has an atomic mass of 1. So 1 proton, 0 neutrons. So this would be active in the NMR. If we look at carbon-12, how many protons are in carbon-12?
Oh.
So six protons. And if it's carbon 12, how many neutrons does that mean it has?
12. 6.
So 12 is the mass number, right?
Gotcha. And
then when you're looking at your atom, so you have protons, neutrons, and electrons, right? Electrons don't add anything to the mass of that atom. Yeah. So basically your mass number is just your number of protons plus your number of neutrons.
Gotcha. Okay.
So 6 and 6. So because we have even numbers of both, carbon-12 is inactive in the NMR.
Okay.
Okay? Does that make sense?
Yes.
All right. He could give you any, I know you have your take-home, but in terms of like the final, he could give you any type of atom, and he would want you to know that. Okay, I'm going to get rid of this. Let's see if this one works better. Okay, so when you have a readout, if this is our starting point, okay? Your readout always starts on the right and then moves to the left. Okay. So there are two areas that you need to know. So if things are pushed more towards the left, that's considered low field or down field. If things are closer to the right side, that is the high field. You can also say up field. Now, peaks will show up depending on how shielded the nuclei is, okay? So we'll talk a little bit more about what shielding means, but the more shielded, wait, no, I'm sorry. I wrote that in the wrong place. So shielded, you're going to be closer to the right side.
Okay.
De-shielded, closer to the left side. Shielded looks like it's spelled wrong, but it's not. I think I wrote it enough today that it just looks weird. So let's talk about what shielded means. So again, we're looking at the nuclei here, right? What surrounds the nuclei?
What do you mean?
So like when I draw an atom, usually I draw like rings out here. What are in these rings?
Orbitals, electrons.
Electrons, exactly. So these electrons kind of act like a shield, okay? So the more electrons you have, the more shielded it is. So you can think of this as more electrons, less electrons. When I was kind of pointing towards, this as our starting point, they typically use TMS, tetramethylsilane, as kind of the baseline for this. If we look at what TMS actually is.
They use it as the baseline for the starting point?
Yes.
Okay.
So we compare everything to TMS. So basically we have a silicon atom surrounded by methyl groups. So CH3, 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 CH3.
What did you say? Tetramethyl?
Silane. S. In terms of, questions that he can ask, typically he will accept TMS.
Okay.
Or if you do the molecular formula, he'll usually accept that as well. Now, the reason that we use this is because the silicon here, because we have these methyl groups surrounding it, the silicon nuclei is very shielded, okay? So it's, I know there are things that are technically more shielded that you could use, but most, at least, in the past, they've used this compound because it is so shielded, and you can kind of compare everything else to it. So you use this as a starting point, and depending on where your shift comes from, you can determine like exactly how shifted the molecule is that you're looking at. When you are trying to, so let's, as an example, so the distance from this peak to the TMS line, this is referred to as the chemical shift. And this helps you determine what exactly is giving you that peak. You know, is it this type of hydrogen or is it this type of carbon, for example?
Do we need to know like where it measures from? Like the top of the peak, the middle, does it matter?
Don't worry about that. These peaks are actually, when you are looking at a real one, it's pretty much like that.
Pretty much a line.
Yeah, pretty much. It doesn't, it's not as exaggerated as the way I've drawn it. Let's see here. Now, I don't know if he's asked this before, but we should talk about it. So one thing that I didn't fully explain here. So in your NMR, you have this electric field, okay? And we talked about how we're sending radiation to these nuclei. Now, we can increase the frequency of that radiation or decrease it. By doing that, so say I double it. So this is before I double it, and say I increase the radiation, I multiply it by 2, and the peak comes up here, ignoring this one.
Mm-hmm.
When you have, by changing the frequency of your radiation, you're going to change the chemical shift, or the distance between TMS and your peak. So to kind of account for that and balance that out, I don't think he's going to ask you this, but you know, I'd rather be safe than sorry. So the chemical shift, you take the distance, so this,
mm-hmm.
and you divide it by the frequency that you're using. That just gives you, you know, it's a value that you can then compare, because, you know, if I do a procedure and I'm using, you know, X frequency, and you use the same sample and you use Y frequency, our distances will differ.
Mm-hmm.
But when we control for the frequency, we're going to get the same chemical shift. Okay.
And the chemical shift is what tells you what
Yes.
it is.
Yes. Okay. All right. So let's talk a little bit more about de-shielded. So there are certain things that can de-shield a nucleus. And one of those is electronegative atoms. Can you give me an example of a very strong electronegative atom?
Fluorine.
Chlorine, great. So all those halogens. Ooh, even nitrogen and oxygen would be considered, you know, in this case. So because these atoms are electronegative, okay, that means that they're pulling electrons, they're trying to take electrons from elsewhere. If we have, so for example, okay, so I'm adding chlorine groups as I go down here. So the hydrogens and the carbon nearby, if there's a carbon-13, are going to have their electrons pulled closer to that chlorine. So we're actually going to see the peaks of these shift more and more downfield. So the more electronegative atoms you have, the more de-shielded that nucleus is. I know it comes up here at some point, but I'm wondering if it's in a different chapter. Another thing that can affect this are pi bonds. Okay, where do you find pi bonds?
Between two carbons and a double bond?
Excellent. Okay, yes. So if you have double bonds or triple bonds. Okay, so
one of them is a sigma and the rest are pi.
yes, yes. So pi bonds themselves act very similar to electronegative atoms in that they pull the electrons closer to them. So anything that is near a double bond or near a triple bond is going to be de-shielded and show up further downfield. Okay. Does that all make sense?
Mm-hmm.
Okay. Let's talk about equivalency.
He's not going to ask us, like, I don't know, give us the picture of a chemical shift and say, like, what possibly could this be?
No,
okay.
no. Yeah, no. That would be mean. Let's see. Okay. So, okay. So we're going to talk about equivalency. So when you're looking at atoms, let's just do hydrogens for right now. Say we're doing hydrogen NMR, or proton NMR. You can have equivalent hydrogens or non-equivalent hydrogens. The easiest way to kind of see this, you're looking at what those hydrogens are connected to and what that's connected to. So if we look here, these hydrogens are connected to a carbon that has 3 hydrogens as well.
Mm-hmm.
So these hydrogens are considered equivalent. So if we were to run this through a proton NMR, we would only get 1 peak even though we have 6 hydrogens, because all of those hydrogens are going to absorb the radiation the same way because they're chemically equivalent. Okay. Now if you were to...
What if it was a carbon bonded to, I don't know, something other than a carbon?
So
would it matter?
If it was any, so how about this? If we were to do okay, so now we have a chlorine in there. Okay, so these hydrogens would all be equivalent, and these two would be equivalent, but these would be non-equivalent. So essentially, if we were to put this in the NMR, we would have our 1 peak that would represent those 3 hydrogens,
mm-hmm.
and we'd have a peak further downfield because this chlorine is going to de-shield those adjacent hydrogens.
It's going to pull.
Yep.
Okay.
Yep. So this would correspond to these, and this would correspond to these. So even though you have 5 hydrogens, you're going to have 2 peaks because you have 2 groups of non-equivalent hydrogens.
Okay.
Okay. Equivalent, non-equivalent.
So it's not necessarily how many they are or where they're placed, it's how strongly they pull.
Exactly.
Okay.
Yep. Let's see here. So if we were, for example, this is a hard one. Okay, so you were given this molecule. He could ask you how many, non-equivalent hydrogens there are, or another way of saying this, how many peaks would you expect, okay?
Okay.
So this one is probably the toughest one that you could see.
Okay.
So again, you're looking at, it's kind of like degrees of separation.
Mm-hmm.
Okay. So how many hydrogens would this carbon have?
That one's gonna have 1.
Okay. Here?
2. 2. 2. 1.
Okay. All right. So let's try and find hydrogens that are connected to similar things. So I typically like to start with substituents.
Okay.
So these 3 hydrogens are bonded to a carbon,
Mm-hmm.
and the carbon that they're bonded to is a CH.
Mm-hmm.
Okay? CH3, this carbon is bonded to a CH.
Mm-hmm.
So these hydrogens would be equivalent.
Okay.
There are no other CH3s, so these ones would only be, you know, grouped together. So
They're
that's
equivalent to each other.
yes, yes. So that's one set. Okay. Now,
So would those show up as the same peak?
yes, so that would be
Okay.
1 peak. Okay. So then if we move in, so we have a CH that has a substituent off the ring, a CH2, and a CH.
Mm-hmm.
Here we have a CH with a substituent, a CH2, and a CH. So these hydrogens will be equivalent.
Mm-hmm.
There are no other CHs. Okay?
Mm-hmm.
So far so good, right? That's not done.
Yep.
The tricky part is when you get to these ones, because if you look at it at first glance, they're all CH2s. However, this CH2 is bonded to a CH and a CH2. This CH2 is bonded to 2 other CH2s. So this one and this one will be equivalent because they both have
Mm-hmm.
similar connectivity, but this one would be on its own.
Okay.
Okay? So I'm running out of colors, but equivalent, equivalent,
Mm-hmm.
and then these would be on their own.
Okay.
So we would expect 1, 2, 3, 4 peaks here.
Okay. Does the concentration of, like whatever we're looking for, affect the peak?
So we'll get into that when we talk about integration.
Okay.
So do you mean like the height of the peak?
Anything.
Okay. So the number of hydrogens corresponds with the height of the peak.
Okay. Yeah, I would assume if there's more, the peak's gonna be higher.
Yeah. Well, it's not. There's a little bit more to that, but
Okay.
I think that's the best way to kind of think of it before we get started. But this part makes sense. You can see where the 4 different groups come. Okay, great. So if we were to look at this one. How many peaks would you expect?
2.
Okay, walk me through it. Where do you see your 2 peaks?
So I put the carbon at the top by
Okay.
itself because
Okay.
it doesn't seem like there's anything else.
Okay, so that's
Like
on its
it.
own. And actually, since we haven't quite gotten into, we'll call these, okay?
Okay.
Where's your
Oh
second
wait,
peak?
would it be 3 peaks instead?
It would be 3
Yeah.
peaks, yep.
Because then you go down the CH3s on top are only bonded to the 1 carbon and then the CH3 on the bottom, but the CH3s on the bottom are both bonded to a CH3.
So be careful. So this carbon
Yep.
has no hydrogens. Because we've got 1, 2, 3, 4. So the carbon in this ring has no hydrogens.
Okay.
Do you see that?
Mm-hmm.
Which, because this is an example from, so, sorry, I'm like, trying to simplify it. Let's focus on the carbons, because you can do carbon 13 NMR as well. But, so we have 1 carbon here.
Which one is most used with NMR? Carbon
So
13?
we're going to talk about some problems that you run into with proton, so hydrogen NMR, that carbon 13 NMR actually helps to get rid of. The issue is, and we're going to talk about, you know, so carbon 13 is an isotope, right? And it's not as prevalent. It's only about 1% of the, so you kind of have to use both.
Okay.
So there's like pros and cons of both, I guess.
Okay.
So this carbon, like you said, is definitely on its own. these carbons are all identical because they all have H3s and they're connected to carbons with similar connectivity. So then finally you would have these carbons as a third. So you'd have 1, 2, 3 here. Okay, good. When he's doing equivalency with you guys, it's probably going to be something pretty generic, easy to see. So if there's any difference in terms of, electronegative groups, or if they're connected to, you're probably going to see connected to a halogen or connected to an oxygen.
And the electronegative group shows first.
So
or they come out at the same time.
Be careful. So we're still only, so for example, when I drew these two peaks, I'm referring to the hydrogens.
Right.
So the chlorine is affecting how these hydrogen peaks are showing up. So this is an electron withdrawing group, right? It takes electrons. So would it be more shielded or de-shielded, these hydrogens?
More electrons is de-shielded. Right?
Right. So the chlorine, the wording gets tough. So the electrons are being pulled towards the chlorine. So these hydrogens are de-shielded. So they're going to show up in the low field.
Okay.
So the chlorine itself is becoming more shielded. But in Proton Nmr, we only see peaks for hydrogens.
Okay.
I know it's a little confusing. Okay. Let's kind of shift a little bit into carbon-13 NMR. Well, crap. Let's talk about some of the issues that you have with Proton Nmr, because the reasoning behind carbon-13 is because it gets rid of some of those issues. All right. So when I was drawing this one, so we have equivalent hydrogens. I drew it as one single peak, right? So that looks nice, but it's not always the case, especially when the hydrogens are close together like I've shown them here. So when you have equivalent hydrogens right next to each other, adjacent, you get something that's called spin-spin splitting.
You talked about this, yes.
Okay, so instead of one nice peak, you end up with this multiplet. Okay, so what I drew before was a singlet because it was one single, but here I've drawn actually a triplet. So you have 3 peaks coming up, and that has to do with, because these hydrogens are equivalent and they're so close together, there's some interference, and so it just ends up being a little bit more complex of a readout. You can see here, for example. So here, these 3 hydrogens are all, so we end up with this couplet here. These 2 hydrogens, you get something very similar.
Is this the one that gives the racemic mixture? One of them he had said gives the racemic mixture. I know he likes that, so
I'm trying to remember what he was referring to. I don't think it was this necessarily. But maybe I'll keep looking as we're going through. I haven't seen that come up yet. I'm wondering if it's just in his notes. I don't know if she put it in her notes. Okay. So there are 3 different types indicating how far away these equivalent hydrogens are. So if the hydrogens are on the same carbon, okay, this is referred to as geminal. For people that are familiar with horoscopes, Gemini refers to twins, right? So coming off of the same carbon, these are geminal hydrogens. And when they are adjacent like this, so we have carbons right next to each other, this is vicinal. So hydrogens on adjacent carbons. This is really when you see the spin-spin splitting. If you have a carbon in between, you really don't see much of any spin-spin splitting with this. So as long as you have some non-equivalent hydrogens in there, or even if you had an oxygen or electron withdrawing group in between them, you really don't see much spin-spin splitting. But if they're on the same carbon or right next to each other, you get this, you know, multiple peaks right next to each other. He may talk about this. It goes, I think, one step probably too far, but let me redraw this just a little bit so it's more accurate.
So the vicinal is going to give us a singlet, and the geminal is going to give us the multiple?
No, these will both give you multiple.
Okay.
Okay. The book goes into detail as to, you know, to figure out how many peaks to expect. I don't think you need to worry too much about that. But you will typically get multiple peaks, you know, whether it's a triplet, quartet, or higher with either of these. Once you put in a carbon in the middle, you should expect just one single peak.
Okay.
So this is where it gets a little funky, but there is this thing called the coupling constant. And essentially, you're just talking about the distance between your outer peaks and the center of this multiplet. So this is the coupling constant. You may see it at, like, you may talk to it about it as J. I don't think you're going to get too many questions on this, but this can help you figure out the orientation. So whether it's geminal or vicinal. Okay. You won't have to do any math, but I think just being familiar with the term will help. Okay.
And how will we know if it's geminal or vicinal? You have to do math. You can't just look at it and
no,
say,
yeah,
okay.
no. So don't worry about that. Don't worry about that. But just knowing that this is a thing, you know, the distance does matter. It's not, you know, just, you know, whatever happens, happens. There is a point behind it. So I want to shift a little bit. So this is, again, in Proton Nmr. You see this spin-spin splitting. So the biggest reason for using carbon-13 NMR is you don't have this. And we're going to talk about why, because that's really important. Okay. So we know that carbon-12 is inactive in the NMR, right? Because it has 6 protons, 6 neutrons. Carbon-13 is active because we have 7 neutrons. So because we have an odd number of neutrons, we see carbon-13. We talked about how this one is a lot more rare. It's only about 1%. And this fact is why we don't see spin-spin splitting. So I'm going to do, so we had, if we were looking at the hydrogens, right, for this one, we see that these hydrogens are equivalent, okay? If we're looking at the carbons, say one of these carbons, or for these carbons to be equivalent in the carbon-13 NMR, you would have to have both of them be carbon-13. Because carbon-13 is so rare, it's extremely unlikely that you will have 2 carbon-13s next to each other. They will always at least be separated by one other carbon. So because carbon-13 is so rare, you don't have the concern of having 2 equivalent carbon-13s next to each other. Okay? So by using this, you get rid of this, you know, kind of confusing multiplet, and you just get one single peak. So it's a lot easier to read carbon-13 NMR readouts. Okay. Okay, so that's, you know, carbon-13 NMR and why what you need to know about that. Okay.
Does it show differently at all, like the carbon-12 and carbon-13? Like, do they have different peaks, or do they?
So would carbon-12 show a peak in the NMR?
No, because it's inactive.
Right, exactly. So that's why it's so much simpler, right? It kind of simplifies everything.
So you're only working with one.
Exactly. Yep. Okay, so you had mentioned, you know, does the height matter, or, you know, how do you figure out, you know, how many carbons, you know, we're actually talking about? So, have you had to take calculus yet?
No, I don't have to take it.
Okay, so there's this thing called integration, okay, and it's kind of like 50% of what calculus is. And really all integration is if you have a line on a graph, okay, integration is just determining the area underneath that graph.
Okay.
Okay? So we can use integration to figure out the ratio of carbons that we're dealing with. So you can kind of see it on her notes, but essentially, I'm going to try and make it as accurate. Okay, so these, you know, points, this line here, we can calculate the area underneath them, and it gives us a ratio. So in her example, the ratio here is 3 hydrogens to 2 hydrogens. So we know, and this peak is given to us by 3 hydrogens. This one is given to us by 2 hydrogens. And because this one is shifted, there must be an electron withdrawing group near these 2 hydrogens to make it.
Gotcha.
Okay, so that's how you can get more information from this. The last thing I probably should have talked about at the beginning, I kind of forgot, it's kind of one of those, like, how does the NMR work type things. So there is a time scale for this. All that means is if there's a change occurring in the structure, it needs to take at least 1 second to take place, or the NMR isn't going to figure it out, or isn't going to notice that the change occurred. Yeah, read it, perfect. So 1 second. The example that she gives, so when we were talking about cyclohexane, has the different chair introversions, that takes place in less than a second. So NMR can't pick up that shift, that change, in a sense.
So what does it show as? Anything?
It won't show any change at all. It'll show the same peaks as one versus the other.
Okay.
So in terms of questions that he'll ask, he could just ask you, what is the time scale of the, you know, an NMR? Or he could say, so-and-so occurs in under 1 second. Will this change show in a carbon-13 NMR? Or whatever. So it has to take longer than 1 second for the NMR to pick it up. Okay. Now, that's pretty much chapter 10 in a nutshell.
Okay.
Feeling okay with it? Does it make a little bit more sense now? Okay. Do you want to talk about structures?
Yeah.
Okay.
That's what our quiz is on tomorrow.
Right. I have some.
I can't tell if he's giving this to us as like a freebie, or if he's giving this to us as a challenge.
If you have a good understanding from regular chemistry and you've been paying attention, I feel like this quiz should be, in a sense, a freebie.
Okay.
Not that you won't need to, know what you're talking about, but if you've been paying attention, you should have a pretty good understanding already. And I was working with a student earlier today and took some pictures. Let me see. Of just some examples that we can go over.
Like, do you think he'll be asking about all the functional groups, or just the ones that we've really worked with?
So, from what I've talked to other students, it was my understanding that it's what you've gone through already. Because in Orgo 2, you go into aldehydes, ketones, carboxylic acids, all that stuff. So I don't think he's going to put much emphasis on it now because you really haven't...
You've, like, touched on it for
yeah,
like
and
a
in terms
second.
of the naming, like, the nomenclature, you really haven't talked about it at all. And there are some important differences. So we can talk about some of the things, but I don't think he's going to go too much farther. So when I was working with a student, so you've really been working on alkanes with alkyl substituents, halo substituents, so halogens, and cyclic, so cyclic alkanes. You've done alcohols, and then ethers, and you have talked about cyclic ethers. That one was pretty brief, though. But that's really all you've talked about, correct? And you've started on alkenes, but did he say whether he's going to put alkenes on this?
Didn't really say anything. He just said it's on structures.
We'll talk about alkenes just in case, because I know that one he kind of has started you guys on, so he could throw some things in there. So I'm going to do, so you said most of it is going to be...
You didn't really say. He said he might give us the structure and ask us to name it, or he might give us the name and ask us to draw the structure in whatever form we choose.
Okay, all right. So I'm just going to do some examples. Let's start with these three.
Okay.
Okay. So I don't know where your confidence level is with naming. Do you want to try and go through these on your own? Do you want to walk through them together?
Well, I know the first one is... We can walk them together.
Okay.
I know the first one is cyclopentane.
Okay, that's part of it, yeah.
And then we've got a methyl group on 1 and 2.
Okay.
So it's going to be dimethyl, but do you need to put the numbers in if you're saying dimethyl?
You do, because dimethyl could mean what in here?
3 or 1 and 5, yeah.
Yeah.
So it'd be 1, 2 dash dimethyl cyclopentane.
You got it. Excellent.
Okay.
Very good. Walk me through how to draw this one.
Tetramethyl cyclopropane. So you're going to do a triangle.
Okay.
For the cyclopropane.
Good.
And tetramethyl, so you're going to have methyl groups, which is the CH3.
Good.
And you're going to put 2 of them on 1 and 2 of them on 2.
Okay. Like that?
Yes.
Good.
And then the last one is cyclohexane.
Okay.
And we have a methyl, an ethyl, and an alcohol.
Okay.
So we're going to put, and it's on 1, 3, and 5. So, like, which do you put first? You go, the alcohol gets precedence, right? Or in the naming?
It does. So
So
first thing I want
cyclo-
to ask you is, how does this change the name?
You're going to take off the A and E and put an OL.
Close. Just the E.
Just the E.
Just the E. So it's going to be hexanol.
Okay.
Okay. Excellent. Now you said gave precedence. What does that mean?
Like, which is named first? Which?
Okay. So be careful with, when I hear precedence, that refers to the numbering, which is absolutely right. So you want to give alcohol the number 1 number, okay, always. In terms of when it's named, that is actually in alphabetical order. So that's a little bit different. The numbering and the order aren't always the same. Okay. So start from 1, and these are both the same distance away, so it doesn't really matter in this case, typically. So you have ethyl here, you said, and methyl. Mm-hmm. Out of these 2 substituents, which would you want to put first in your name?
I would say methyl because it's closest. Well, they're the same distance away depending on where you go.
Right.
So alphabetical order. So ethyl, the E.
Good. So we're going to put this with the ethyl having the lower number. Okay. Okay. So 2. 3. Okay. Mm-hmm. So ethyl comes first alphabetically. So 3 ethyl. 5 methyl. And then, so I've seen it both ways. When you have cyclic like this, and you have something that changes the name, you can put the 1 in. I don't think you necessarily have to, but he's not going to take credit off for putting it in there, okay. So I usually just tell students to put it in there. Okay. It's redundant, but it's rather that
it's 1 because it starts.
Exactly. Exactly. Okay. So 3 ethyl, 5 methyl, 1 cyclohexanol. Gotcha. That's a pretty complicated one. I'd be surprised if you put that on your quiz. Do you want to take a picture of these, or I can erase them? Okay.
Nope. It's all coming back to me once you go over it.
It's just like riding a bike, you know? Okay.
I feel like we've just been so focused on so many different aspects that the basics have kind of been on the back burner. The first one's throwing me off. Okay. Ether is C bonded to O bonded to C?
Yes, so. Absolutely.
Okay.
Okay.
And then propyl or ethyl, we're going to have a CH3CH3. In propyl, we're going to have a CH3CH2CH3.
Say that again, CH2.
Propyl CH3CH2CH3.
So like that?
No, because that one has too many bonds. So
which one?
The ones on either side of the O.
Good.
It's going to go down to CH2.
Perfect. Good catch. I know it's hard when you're not the one writing. Like that?
Yes.
Final answer?
Yes.
Yes. Good job. Great. So ethyl, 2 carbons.
It's just
propyl,
me.
3 carbons. You got it. Very good. Okay.
It's literally just me.
No one else. Thank you. Are you going to physics?
Yeah, I'll see you over there.
All right. How about this one? How would we name this one?
That one is going to be, there's an OH, so it's an alcohol.
Good.
And there's one, the longest carbon chain is, it's going to be 3, no matter where you go. So it's propanol.
Good.
And then does it matter where you start? No, not really, right? Like if...
You tell me.
Maybe we could say 2... 2,2-dimethylpropyl. Is that a thing?
So you're very close. And again, when an organic chemist is reading this, when you say you have propanol and 2,2-dimethyl, the OH has to be on the first carbon. Even if it was over here, this would be the first carbon. There's no other place for it on the second carbon. But for good measure, don't forget to put in
1.
Yep. Especially for straight chain. You can probably get away with it with cyclic, like I said, because it's kind of expected to be number 1. But in a straight chain, even though in this one there's no other place for it, I would recommend just putting it in the one for telling you where that alcohol group is.
Possible to have, yeah, because it's possible to have an alcohol group on like a 3 or a 4.
Yes, exactly. Yes.
Okay.
And then how would we name this one?
That one is dimethyl ether.
Excellent. Very good.
Okay.
Feeling pretty good?
Yeah, I feel
Okay.
good about these.
Yeah.
I just needed a slight review.
I have more examples. I don't know how pressed for time you are.
I'm pressed. I got it. I have
Okay,
class in
that's what I
Western
figured.
14, so.
Oh, yeah, you're very pressed. Okay. So, yeah, I think you're going to do fine tomorrow.